All right, so our last lecture here for chapter 31 and kind of rounds out our semester is finishing up what's left in chapter 31, which is the electromagnetic waves. So in your textbook has a very thorough and like I said before, very interesting derivation of the electromagnetic wave, and it uses pretty much all the laws we saw so far. It uses Faraday's law, Gauss's law, Ampere's law. Okay, it uses all that to derive this equation. So I just want to show you a couple of highlights from that derivation, and then we'll kind of move on from that. So let's start with this. So like I said, I'm not going to do a whole derivation for this. But let me have an axis here. I should have done that earlier. Okay, so we have our different axes. We have our, there's a y, x, z right here. And let's say that we have an electric field kind of varying in direction and magnitude. So you might have an electric field looking something like this. I'll do this in red. Just along the xy plane, or so plane like this. So here's our okay, so it's really easy to kind of create this. All you need to do is have an antenna, a transmitting antenna, kind of hooked up to an AC power supply, and that antenna will then create this electromagnetic wave. Okay, so we're just looking at the electric field part, and we can kind of connect them, and you can kind of see like not this. Can I see that cosine curve or a cosine curve? And I'll keep going. Okay, so we have these electric fields here, all changing, and if that electric field is changing, it's then going to create a magnetic field. So this is where I kind of skip the derivations here, and I'm going to just show you a couple of partial derivatives. If you don't know what partial derivative is, don't worry about it. It's not terribly important. Okay, so we have dEy over dt. So this is just taking the time derivative of the electric field with respect to y. That weird shape there almost looks like a 2. It's just think of it as dEy over dt, right? It's a time derivative of the y component, and the faster this is changing, right? As the electric field changes, as the y component of the electric field changes over time, this gives us a relationship to the magnetic field in the z-axis over time. Okay, so this is what I've been talking about earlier, and it takes some work to see that. You have to use Faraday's law, and I think you actually use Faraday's law twice, and Ampere's law. So you kind of have to mess with it with the different laws that we've seen so far. But so what this tells us here is as the rate of change of the electric field in the y-axis to the rate of change in the electric field, in the magnetic field, rate of change of the magnetic field in the z-axis. Okay, just in opposite directions, right? You have that negative in front. So as E changes, as E increases its change, rate of change, B, the magnetic field, is also going to increase its rate of change. Okay, so that's one key takeaway there, that the rate of change are related to each other. Oh, actually, this is what happens when I do not go through derivation. It's actually not dx over dt, or not dEy over dt. It's dEy over dx. That makes more sense. All right, so let me change this. So rate of change. I gotta be kind of careful here. Rate of change. There's a rate of change of the electric field. Let's see. I'll put it this way. the electric field changes over the x-axis. I'm going to have to reword this. Field in the z-axis changes over time. Okay, so this is even more trippy. Okay, so as if the magnetic field is changed, or the electric field in the y component changes over position, which it is, you can see that in the graph there, that telling us that the magnetic field is going to be changing over time. Okay, so we do have a connection there between how the electric field is changing over space and how the magnetic field is changing over time. All right, so we do a couple, so that's one key takeaway here that we would have seen from derivation. Another key takeaway is this equation here. So again, this is a partial, so think of it as derivatives, the d squared ey over dx squared equals mu 0 epsilon 0 d squared ey over dt squared. All right, so now to get to this equation, let me make this a little bit neater. Okay, to get to this equation, yeah, even more, a lot of differentiating, had to do a couple substitutions using Ampere's law here. But what this is, and you haven't seen this yet before, I don't think, in your classes. This is essentially the wave equation. Anything that has this form is going to be some kind of wave. So this is telling us the electric field is acting as a wave, changing sinusoidally over space and time. Okay, and not only that, there's a speed. It has a speed, and that speed is related to whatever this constant here. Okay, so another key takeaway is the speed of the wave is equal to. This is not quite equal to this, but I'll show you. So the speed of the wave, v. Let me do this in a different color. Is equal to 1 over square root of those constants. Okay, now, if you plug that into your calculators, something really interesting happens. During this derivation, we're just using our laws that we saw, Ampere's law. And when you use Ampere's law, you do have to use a modified Ampere's law that we saw with Maxwell with a displacement current. All right, so we're using Ampere's law, using Faraday's law, all these laws we're using, we get this relationship. If you and you get mu 0, which is a constant, right? 4 pi times 10 to the negative 7, epsilon 0, which is 8.85 times 10 to the negative 12. So we're using these constants, and what we get is the speed of light. Right? You plug that into your calculator, you get c, which is the speed of light, 3.00 times 10 to the 8. And I think that's the most fascinating result from this. You get these two constants that we've been using kind of independent from one another, right? One for the electric field, one for the magnetic field, and you get the speed of light, which is, this little fact is kind of the basis of special relativity, because it depends on these physical constants. The speed of light should not be changing, no matter what your reference frame is, because those constants stay the same, right? They're just constants. Okay. So we get the speed of light there. Electric field is a wave. And we also do see the same thing for magnetic field. So I could do, again, through some substitutions, we get this. So that's the same thing as writing, let me finish writing, I'll tell you. So d squared bz over dt squared. Okay, so again, we get the same form, same form as before, right? Oh, this is supposed to be an x. Okay, same form as our electric field. The only difference here, if you compare them, well, you have this constant, so I just substituted, right, using this equation here. I guess this should be a c, not a v. Well, v is just the speed of the wave, but we're talking about the speed of light. I'm gonna write this as c. Okay, so I just make a substitution there. Instead of these constants, I have 1 over c squared. But look at, this is the electric field in the y, gives us a wave, but now we're talking about magnetic field in the z component. So we have a magnetic field that's also a wave, and it's going to be looking like this. Right, along the z component there. And so this will be my magnetic field. So, so the magnetic field is in the z-axis, and the electric field is in the y-axis, and they're both waves. So let me show you kind of a picture of that to kind of see what's going on. Okay, so here's what I'm talking about. This is an electromagnetic wave. You see the electric field is constantly moving, right? It's moving along the x-axis, but it's also varying over time. And what you see at all times is that the electric field is perpendicular to a magnetic field. Okay. So this is what these waves, these equations tell us. These differential equations are telling us that when we're talking about these electric fields and magnetic fields changing, they're almost self-propagating. The change in electric field is giving us a change in magnetic field, and vice versa. A change in magnetic field is giving us a change in electric field. So as long as they both keep changing, this wave will continue. And that's why the electromagnetic waves don't need to go through a medium. They're not dependent on moving through water or some kind of material. You could have electromagnetic waves traveling through space, through the emptiness of space, because, well, it self-propagates. It creates a next step in the wave, okay, by itself. Okay. All right. So let's go back to our slide here. So this is what we're seeing here. Now there is if I look at the max values, or even not the max values, but the electric field is related to the magnetic field in a more direct way. You can kind of see it with, we know they're related in terms of their change, right? How one changes affects how the other changes. And we see like they're waves, but the actual magnitudes are also related. And this, again, takes a little bit of work, takes a little bit of doing some integration. I know that, like, again, you could look at your book to see that exact that derivation there. Okay, but let me see if I can fit off to the side here. Okay. Okay, so it turns out if you take the ratio of the electric field over the magnetic field at any time, E over B at any time, you will get, that will always give you a constant ratio. And guess what that constant is? Well, it's the speed of light again. C. Okay. So again, really interesting that this electric fields and magnetic fields are kind of working together to give us, something that we see all the time, right? Light, these electromagnetic waves. Okay, so one thing that this has too, we're talking about electric field. We know energy uh, is like in a capacitor, energy is stored in an electric field. We know in an inductor, energy is stored in magnetic fields. So right now, for electromagnetic waves, we have electric fields and magnetic fields, which must mean there's energy there. Okay, so let's talk about this energy. So let me go here. Energy in EM waves. Okay, so energy, to talk about energy, we could look at a cross product here. I'll kind of introduce energy by talking about this. It's about the direction of the wave. Okay, we could get the direction of the wave by looking at a cross product of E and B. So we take E cross product B. Okay, just the direction here will give you the direction of the wave. Okay, so let's go back to our previous slide. If you do E cross B here at any point, doesn't really matter where you do it. You put, do the right-hand rule. What you'll see is that the direction of the electric field, or the direction of the electromagnetic wave, you should always get going this way. Okay, so that is our direction of the wave. So in this case, it would be going in the I hat direction. Okay, and again, you just do E cross B at any point, wherever the electric field is, the magnetic field would be going, perpendicular to that, and you should always get your middle finger pointing to the X, right? So if you want specific instructions, I can give it to you really quickly. Your thumb should be pointing in the direction of E, since that's your first vector in your cross product. So put your thumb in the direction of E. You put your index finger in the direction of magnetic field, and remember your middle finger is perpendicular to your palm. Your middle finger here pointing out is your speed, is your direction of the wave. Okay, that's the direction the wave is going. Okay, so this gives us direction of wave, but it also gives us something called the pointing vector. Okay, so let me write down this equation and I'll explain what it is. So the pointing vector, which is usually notated S, let me go blue here. This equals 1 over mu 0 E cross B. Okay, so what does this tell you exactly? Well, this tells you the rate of energy transfer per area. Okay, so essentially watts per meter squared. Okay, so let me put those units here. Okay. Now it is fluctuating over time because electric field and magnetic field fluctuate over time. Okay, but it's kind of it's not only telling you the direction the wave is going, but it tells you how much energy is being transferred per area. Okay, and if we just look at the magnitude of S, we're going to get something like EB over mu 0. Or remembering our relationship, right? E over B is just electric field, or E over B is just speed of light, right? We see that over here, right? E over B. So I can use this relationship here to make a couple substitutions. I could write this as, I could also use this. I'm just thinking here. I could always use this relationship too, right? This one here. So kind of using both of these, E over B equals C, and C is related to our constants here, mu 0 over epsilon 0. If I use these two together and do some algebra here, I will get this equation. So one way of finding the pointing vector is EB over mu 0. I could also do it with C over epsilon 0 E squared, or I could do it with a magnetic field. epsilon 0 c cubed b squared. That's just after making a whole bunch of substitutions with those two relationships that we saw earlier, right? With this relationship here and this relationship here. Okay. Now the issue here is that E is not staying constant, right? The electric field and magnetic field are not staying constant. We saw that they're changing over time. Right back, going back to that electromagnetic wave I showed you guys earlier. So if they're changing over time, you know, this value will change as a function of time. So what we're going to look at is the average value, also known as the average intensity. Intensity, there you go. So this light wave, this electromagnetic wave, has this intensity. What do I mean by intensity? Intensity, go here, is a watts per meter squared, right? That's what I had earlier. That's known as intensity. So the intensity, I, is just going to be my average pointing vector. We're going to do the magnitude of that, which is just 1/2 C epsilon 0. Or I could do either one, magnetic field or electric field, doesn't really matter. But C epsilon 0 E max squared. Okay. All right. So I just want to do one example with this. So the light bulb with, let me say 50-watt light bulb. Is 3.0 meters away from you. Okay, so we want to look at what is the intensity of light at your location from the light bulb and the E and B field, or the max E and B field. Again, at your location. Okay, so this is kind of the idea. We have a light bulb here, so let me draw my light bulb. Okay, and that's shining light. Let me see, what would be good? I'll do like kind of an orange color. Shining light in all directions, and we are standing here. Right, and that distance is 3.0 meters away. Okay, so intensity. Well, we know how to find intensity, but the equation I have for intensity down there is pretty much if you have the electric field, right, you could find intensity. The other way to find intensity is kind of is definition, right? If you look at the units, watts per meter squared. Intensity is just you're taking that power of the, in this case of the light bulb, and you're distributing that power over a certain area. Okay, in our case, that intensity is going to be spread out over, well, the light bulb is going in all directions, right? So you can think of it as this circle. Almost there. Okay, so we have this light bulb, and that circle is where that light is being distributed. Okay, so if we have this light bulb, if that light is distributed over that whole circle, and remember, you got to think about three-dimensional here. It's not just a circle, but it's more of a sphere, right? Light is going out of the screen, behind the screen, or it's going in all directions. So that area here that we have is going to be the area of a sphere, 4 pi r squared. Okay, So we can find intensity really quickly from that. Intensity, so the power is 50 watts, and that sphere that is being spread out is 4 pi, and the radius is 3.0 squared. Okay, so that gives us an intensity of 0.44 watts per meter squared. Okay, so now that we have our intensity, let's use that to find our electric field. Okay, and this is where our equation for our intensity comes in, right? So let me switch over to a different color here. So now intensity equals 1/2. Let's find electric field first. So I'll use this equation, C epsilon 0 E max squared. Okay, so E max equals square root of 2I over C epsilon 0. Okay, so it's just a matter of plugging that into our calculators. Let's see. Make sure I do this correctly here. All right, so I get 18.2 volts per meter. And so that's our electric field. And now that we have electric field, finding magnetic field, it's not too hard. We can use our ratio, right? E over B equals C. Oh man, I got shaky all of a sudden. And so B is going to be equal to your electric field divided by C. All right, and this is what should happen. Your electric field is always, or your magnetic field is always going to be a lot smaller than your electric field. So yeah, I do get a small number there. I get 6.1 times 10 to the negative 8 Teslas, or 61 nanoteslas. Okay, so there's my magnetic field, there's my electric field, and there's my intensity. Okay, so kind of dealing with a little differently with electromagnetic, electricity and magnetism here, because now that we kind of see that there are waves. We have electromagnetic waves here. And in another physics course, you'll dive deeper into that. It's like that third physics course where you talk about optics and light as a wave, and there's a whole bunch of properties that come with light because of that. So it's kind of interesting there. All right, last topic here as we wrap it up is going to be polarization here. Okay, so polarization. Okay, so when we talk about electromagnetic waves, a lot of times we have, let me draw my axis again that I had in the first slide here. All right, so here's my XY axis. Okay, so like I drew the electric field, and let's just look at the electric field. I understand that when I draw the electric field, there's always a magnetic field. If we're talking about electromagnetic waves, there's always a magnetic field perpendicular to that. So let me just draw the magnetic field. Was that kind of understanding kind of in the back of your mind? So we have electric field like this. Okay, so this will be, in of course, the electric field is decreasing, right, and it switches direction and goes and keep going. Okay, so this would be very typical. This is what's called a polarized wave. Okay, so polarized waves have their magnetic field electric field. And I guess magnetic fields, electric fields orientation along one direction. Okay, and if the electric field is fixed along one direction, like here I have the Y component, then your magnetic field will only be along the Z component. Now you also have unpolarized waves. So unpolarized waves will be a little bit harder to draw. Have their electric field going along different directions. All directions, really. It's unpolarized, but I'll put multiple directions here. So it's not fixed along one way. So if I were to, let's say, view light coming towards us, so viewing a light wave coming at us. Okay, and let's make this an unpolarized light wave. Okay, let's say it's coming at us, so we're looking down the x-axis, and if we're looking down the x-axis, we would see we would have our axes looking like this. So we're looking down the x-axis. You see something like that where this is the y and this is the z axis. Okay, so what we would see for an unpolarized wave is the electric field going in all directions. You have electric field going like this, electric field like this. Okay. Okay, so that's the electric field. I guess I could add a couple more just to emphasize here. Okay, so here's the electric field, not just in one direction, right? Pretty much in all directions. You have this electric field. Okay, so here's our two different waves, and we're going to have these waves interact with something called a polarizer. Okay, so a polarizer is very picky about how these waves come in, and we use polarizers pretty often. If you have sunglasses, and they're polarized sunglasses, that means they're only going to accept light, or they're going to only let light through that has a certain orientation. Okay, so all this, like if we have a vertical polarizer, only light that is vertical will come through. Anything else like that's going in any direction will only part of that will go through, and anything else perpendicular, nothing will go through. So let me show you an app that I have here. I'm kind of ready to go. It's not my favorite app, but here you have unpolarized wave on this side. Okay, here's an unpolarized wave. It's going through this polarizer. Now this polarizer, I could rotate this. You see how it's orientated? It's kind of these vertical lines here. It's only letting electric field that is perpendicular coming through, right? And I wish I could get rid of this. Don't pay attention to the second polarizer. Just focus on this first one. So it's only letting light that is perpendicular going through. So all this unpolarized light, most of it stops, and only some of it goes through. So how much of it goes through? Well, this is what our intensity is for. Okay. So as unpolarized light goes through a polarizer, only half the intensity remains. Okay. So mathematically, I'll put it like this. You have your final intensity after the polarizer equals your initial intensity, right, over 2. Okay, that's for polarized light. Okay, so let's go back here. Okay, so unpolarized, you have all this intensity, this brightness here, only half of it will come through after this polarizer. Now, that polarizer, that light is now polarized. You can kind of see it's fixed along one axis. Right, after the first polarizer, you have this polarization, let's say along the y-axis. Right? and only along the y-axis, right? There's no x component there. There's no z component. It's only along the y-axis. Now I'm going to have this light here go through a second polarizer. Now let's see what happens. Right now, the first polarizer is just letting electric fields in the y direction go through, and that's so it's not going to be affected. But if I start to change the angle, let's do it like this. That's kind of hard to see. Notice what happens. See what happened there? Eventually, if I make this 90 degrees, nothing. So this polarizer stops that light. Right? That light can't get through because it has a wrong orientation. If I give it a little bit of an angle, it starts to get through, or just a little bit. Right? And eventually, if I make it 180 again, or vertical again, all the light comes through. Okay, so it kind of depends on that angle. What is that angle relative to my first angle? Right, and if I make this one 90, let's make this one horizontal. My first polarizer is horizontal right there. Then this one, if that's horizontal, then it lets electric field go through again. But if I start to change that angle, it starts to drop. Okay, so what is that telling us? That's telling us that if you have a polarized light going through a polarizer, the angle that it comes in is going to play a key role in what intensity you get. Okay, if you have a polarized light, a polarized light source, what's a good polarized? So your computer screen is a great polarized light source. If you have your computer screen and you want to check whether your sunglasses are truly polarized, all you do is take your sunglasses and rotate them. If you rotate your glasses, you should see the screen go completely black if it's truly polarized. Okay, so take your sunglasses, that's polarized sunglasses, rotate them, and you should see your screen go black. As you keep rotating, you'll see the screen get brighter and brighter and brighter. It gets maximum brightness there. It should still look a little fainted. It's not going to be as bright with the sunglasses or without sunglasses, obviously, but you should see the brightness come back. And as you keep turning, the brightness goes away until, again, the screen is completely black. Okay, because it's stopping at this point. When I have it like this, 180, almost. It's hard to get that 180. There you go. When I have it like this, it's completely stopping any light going through it. Okay. So how much light actually goes through it depends on something called Malice's law. So Malice's law, I can't remember if there's another S there or not. There is. Okay, so this tells us how much intensity light will go through of polarized light. A polarizer. Okay, and I'll write down the equation. So your intensity after the polarizer equals your intensity before the polarizer times cosine squared theta. Where that theta here, careful with that theta. That theta is the angular difference. I'll put this in black here. Whoops. Angular difference between the polarized light wave and the polarizer. Okay. Okay. So that's what we're seeing there. So I do one example with polarizers, and then we've done it. We've covered our topics. Spell something. Polarizer example. No, I think I'm good. Okay. intensity of 1000 watts per meter squared is incident upon a polarizer. Degrees. Oh, the polarizer is at 30 degrees. Okay. Here's our example, and I'll draw this as a picture. So we have, we start off with the unpolarized light. So remember, unpolarized light has electric field going in all directions. Try my best to draw this kind of a three-dimensional. All right. So here's my electric field, unpolarized, going in all directions, and let's say it's moving in this direction here. That's this V, and then this is all my electric fields. Okay, unpolarized light. I have a polarizer that says 30 degrees from the vertical. So here's this polarizer. Let me make that a different color actually. And it's 30 degrees from, that means the slots here. Remember a polarizer has these slots that it has to let the electric field through, right? Kind of like this. Right, those are my slots there. Okay, so for our problem, the slots are 30 degrees from the vertical. So if I draw a vertical line here, all these slots are something like this. Okay, where theta equals 30 degrees. Okay, so let's just deal with that first. We're gonna have light go through this. It's unpolarized light. So what this polarizer is gonna do, like we saw in the previous slide, is that intensity is gonna drop by half. And now it's gonna be polarized. So afterwards, let me draw another axis here. The the electric field is only gonna have that 30 degree orientation here. Let's see here. Okay. So let me call this I0 here. We know I0 is 1000. I2 or I1 would equal, since it's polarized light, unpolarized light going through a filter, it's going to be 1/2 of I0, which is 500. Okay, so going back to this is what's happening. Just focus on, don't worry about the second one here. Just worry about that first one. So that first one, that first filter, takes all this intensity from this light and cuts it to just half. And now it has a certain orientation, right? Before it doesn't have an orientation, it's going all over the place. But now afterwards, after the first filter, it does have a specific orientation. Okay, so that's what we see in our example here. So now it has a specific orientation, the 30 degree orientation, and it has this. So it has a 30 degree orientation, it has this much intensity. Now we have another polarizer. Okay, and this one says the second polarizer has an angle of 60 degrees. Okay, so that's going to be more of a, I'm not drawing super right. So 30, angle is 60 degrees. Okay, so now we are going to have a light coming through it. Right, so my electric field is going to look something like this now. It's going to be a little smaller because the intensity is a little weaker. Okay, but now the angle is 60 degrees here. Okay, so what is the intensity? So let's call this I2. So I2 is going to equal what we had in I1 just before the second polarizer, cosine squared theta. So I1 is 500 watts per meter squared. And then cosine squared theta, well, what's this theta? Well, the theta is, remember, is the angular difference, not just, it's not the 60. It's the difference between 60 and 30, right? The difference between these two angles. So in that case, it's going to be 30. So cosine of 30 degrees here. Okay, and this gives me my final intensity. So I have 500 watts per meter squared times cosine 30 squared. And I get 375. I'll keep this 2 sig figs. Okay, and that's my intensity. All right, so we would not have seen this behavior if we did not treat light as a wave. All this comes from, well, we had to start with our different laws, right? Faraday's law, Ampere's law, Gauss's law. All those things played a role in us seeing electromagnetic waves as they are, and without the displacement current, and if you look through the derivations, we would not have seen this without Maxwell's displacement current. So now that we see all these different behaviors that couldn't have been explained otherwise. So kind of interesting, we use our laws that we talked about throughout the semester, and we get this fascinating behavior of light, right, of electromagnetic waves. All right, so that completes chapter 31. We've got through our content. Now let's start focusing on our exam.